Okay, this is a review for Exam 1. You can, if you want to play along with the questions, you can pause the video and see what you get right, or you can just, watch it and take notes, whatever, however you want to do it. Okay, so let's talk about the basics of waves first. What kind of wave is sound? It is a longitudinal wave, not a transverse wave. What is wavelength? It's the distance covered by a wave until it repeats. So if you imagine like sound coming out of my mouth, it is like in a wave. Well, it's actually right. It's actually sound pressure wave. So it's just like just like condensation and rarefaction moving out. But we can think about it as like we can model it as a sine wave. So you can think about this as moving up, coming down, and then right there it's going to start another wave. And so that is the wavelength. The length of a wave, the distance of a wave until it repeats, the distance it actually covers until it repeats. So these are measured usually in length measurements, right? So like feet, meters, inches, things like that. What is period? Oh, whoops, I shouldn't have gave that away so quickly. What is period? The time it takes for a wave to repeat. So this is just in time. How long does it take for the wave to repeat? So instead of looking over distance, if you kind of look just in one spot, so like if you're just observing right at my mouth as I'm talking, there's a time that it takes for this to happen, and then when does it start over again at the mouth? And so that's like a time measurement. So wavelength is an actual distance measurement. It's the distance covered by the wave until it repeats. Period is the time it takes for the wave to repeat. And then frequency is the number of cycles in a given amount of time. So we chop the time up into some metric and then look at how many cycles are inside of it. Hertz is the one that we tend to use. For our class, we're going to use Hertz. Most of the time in acoustics, we use Hertz as well. Hertz is cycles per second. Beats per minute is like another type of frequency. What is the relationship between wavelength and frequency? It is inverse. So if you think about a longer wave, which means you're going to have a bigger number. So a longer wave is going to have a bigger number, covers more distance. Let's say 300 centimeters, 300 millimeters it covers. And that means that it's going to be a very low frequency, so 5 hertz or something like that. That's probably wrong, because I'm just coming up with those numbers as numbers, not in any like relationship. But anyway, so 300 meters, and then it's going to be a really low frequency, 5 hertz. If you scrunch that distance down together and it's repeating really fast, doesn't take very long to repeat, this is going to be much smaller, so it's going to be maybe 10 millimeters, and that's going to have a much higher frequency, let's say like 1,000 hertz, something like that. So it's an inverse relationship. And then what about the relationship between period and frequency? That's inverse as well. So longer time that it takes to repeat is going to be a lower frequency. So let's say you have 200 milliseconds is a 5 hertz wave. 2 milliseconds is a 1,000 hertz wave. So it's an inverse relationship, which then means that the relationship between wavelength and period is like a direct relationship between the two. They just correlate. perfectly, assuming the airspeed doesn't change. But so longer wavelength is going to be a longer amount of time. Okay, what about fundamentals? It says fundamentals behind my head. I see right now it just says fundamen, which is like, I don't know, a group of dudes that bring a bunch of like melted cheese. Maybe that's fondue men. But anyway. So how are waves combined? It's additive. You just kind of add the waves together. They get added together in the air. They reach our ear as added together. So you can have a speaker play 200 hertz, 400 hertz, and 600 hertz at three different speakers. One plays 200, one plays 400, one plays 600. They will add together in the air, and they'll reach you as one complex wave that oscillates at a certain frequency. So if you do have that, 2, 4, and 600, what frequency does that wave repeat at? It's 200 hertz. You'll see little things in there that are kind of like cycling at about 600. You'll see little things that are cycling at about 400, but the entire wave repeats at 200 hertz. What is the fundamental frequency? It's the lowest frequency of a grouping, assuming that the grouping is all harmonically related. One of the reasons we call it the fundamental frequency is because the whole signal repeats at that lowest frequency. So just like we're talking with the 2, 4, and 600, if they're all playing, the whole wave is repeating at 200, even though there's little things that are oscillating at these other frequencies, the wave isn't repeating at anything but 200 hertz. And so it's the fundamental frequency. It's the fundamental frequency of the entire combined wave. What are harmonics? They're integer multiples of the fundamental frequency. So you take 200, you multiply it by integers, which is like, whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Those are the harmonics. So if you have 200, it's 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600, 1,800, 2,000, and so on. What is the fundamental period? It's the period of the fundamental frequency. Nothing too crazy there, right? It's just, you have a fundamental frequency, it has a period, and then fundamental is just kind of referring to the fundamental frequency. So what's the period of the fundamental frequency? That's all that means. If you get a question on the exam that asks for the fundamental period, and it's one of those like, just gives you frequencies, you have to compute period from frequency. So figure out what the fundamental frequency is of a group of frequencies, take that, and then convert it to period. Definitely make sure that you're reading what the question is asking. Don't get confused, fundamental frequency and fundamental period. Just because it says fundamental doesn't mean that it's going to be frequency every time. So make sure you read the whole thing. Okay, let's talk about resonance. What does it mean to have a resonant frequency? This is kind of a weird question, so like if you just have a conceptual idea of this, that's okay. But it just means that a frequency is amplified by the cavity. So a resonant frequency means that whatever that thing is, it doesn't have to be a cavity, it can be a cavity. So like my earbud case has a space inside. That's a cavity. It has a fundamental frequency. But you can take like closed stuff and that has a fundamental frequency too. Closed like solid stuff. So like my cell phone has a fundamental frequency. This coaster has a fundamental frequency. Everything has a fundamental frequency. So it's just a frequency that's amplified by an object. I say cavity because we're dealing mostly with the pharynx, and that's a cavity. So we're looking at, the speech tube, and that's why I say cavity. But it's more true to say that it's amplified by the object. So there's certain frequencies that match the resonant characteristics of an object, and those get amplified by the object. That's the resonant frequency. Okay. What else do resonant cavities do? It's the opposite of resonance. They attenuate things. So you have some things that are being amplified. Some frequencies are getting louder, but you have some that are going to get quieter because they're farther away from the resonant frequency. So if my earbud case amplifies 300 hertz, it might also amplify 298 hertz, a little bit, not as much as 300, but a little bit. And it would probably not amplify 200 hertz. It's too far away, much further away. So it's going to attenuate that. Okay, how many resonant frequencies does a mass spring model have? Just one. How many resonant frequencies does a Helmholtz resonator have? Just one. How many resonant frequencies does a tube have? A lot of them. Like an infinite number. We could calculate the 3,000th resonant frequency if we wanted to. That's a crazy thing, but we could. I don't know why you would want to do the 3,000th, but you could. Does that change if it's closed at one end? No. The actual resonant frequency changes, but the fact that there's many resonant frequencies doesn't change. There's still many resonant frequencies for a tube, whether it's closed at one end or open at both ends. Still many resonant frequencies. So on your exam, you'll get like, what are the first 4 resonant frequencies of this? That's the same for a tube open at both ends or closed at one end. Okay, what about, now we're going to continue on with tubes, looking at waves in a tube. A tube open at 2 ends has how many pressure nodes for its lowest frequency? So this is, imagine that drawing of the little tube. How many pressure nodes inside that tube are there for a tube open at both ends? It's 2 pressure nodes. One at the one end of the tube and one at the other end of the tube. I say for the lowest frequency because for any higher frequencies, you could you'll cram more pressure nodes into the tube, but at the lowest, you have a pressure node at each end. And that's because you open out of the tube back into atmospheric pressure. So it's unchanging there. It's got to be a pressure node, pressure 0, atmospheric pressure 0, at both ends of a tube that's open at both ends. What about a tube closed at one end? How many pressure nodes for its lowest frequency? Just one. And that's the open end. So if you're thinking about the pharynx, it's going to be at the mouth. You have a pressure node. Again, because you're opening back into atmospheric pressure. And then down here at the vocal folds, you have a... Let me see if I'm going to give away another question. No. You have a pressure maximum at the vocal folds. Okay. The lowest frequency that a tube with 2 open ends can resonate is how many times the wavelength of that tube? Wavelength is probably not... I think I wrote the wrong term here. The lowest frequency a tube with 2 open ends can resonate is 2 times... Oh, sorry, I just gave it away. Is how many times the length of the tube, not the wavelength, but the length of the tube. That's 2. I just gave it away. What about the lowest frequency a tube with one end closed can resonate? It's how many times the length of the tube? It's 4. Okay. Great. So let's take a look at some pictures of why that is. So we're talking about pressure nodes. And remember, pressure is always drawn in red. Velocity is always drawn in green, at least in this class. I'm not sure that the book is consistent about red and green, but all of my stuff is consistent with red and green, and your exam is consistent with red and green. So red is always pressure, green is always velocity. So we're talking about pressure nodes. This, of course, is a tube that is open at one end only, this end right here. And this is our pressure node. So it opens back out into the air, into atmospheric pressure node. And then here at the vocal folds, we have either a pressure max or a pressure min. It's the place where it's wobbling mostly. It's not a node. It's a place where it's wobbling a ton. So it could be a max. We'll call it a max. So here's a node, here's a max. And the reason why it's 4 times the length is because you go from this node to this max, and if you're looking at a full wavelength, which is right here, we can go up, down, and here. So that's one wave. We've got a node and then a max right here, and that's just a quarter of that wave. So it fits in. The lowest the lowest frequency that can fit in is a quarter, or 4 times the length of this tube. A quarter of a wave. You cannot fit you cannot fit half of a wave into a tube that's open at one end because you have a node and a node. So you can't get a node at this closed end over here. It's always got to be a max. You can get 3/4. So you can start at this node, and you can go here. You can't get 2 in there, but you can get 2. Sorry, hang on. I'm just totally. I said the wrong number. You can get a quarter. You can get half. You can get 3/4, but you can't get 1. That's where I said 2. It should be saying 1. And then you can get 1 1/4. And then 1 3/4, 2 1/4, 2 3/4. Odd numbers, basically. Here's velocity. It's the same basic idea. It's just flipped. So you have a velocity node at the closed end, and you have a velocity maximum at the open end. So again, if we're thinking about the pharynx, you have a velocity node at the vocal folds, and you have a velocity maximum at the lips. And then same thing, this is a quarter, this is 3/4, and this is 1 1/4. And that's for a tube open only at one end. Here's a node. They're calling this an antinode. We're calling it a max. It is actually more accurate to call it an antinode, but we'll just call it max, node and max. And here's the tube open at both ends. Right here. There, now you can see my mouse. So this is a tube open at both ends, and we need that. Remember, again, we're looking at velocity. So when we're talking about pressure, it's a node here and a node here. When we're talking about velocity, it's the opposite, which means we have a max here and a max here. And then closed at one end, it's a quarter. So up here it's a half, and here it's a quarter. Okay, let's do some formulas. Like I said, I'm going to make sure that you have the formulas, but they're not labeled, so you need to know which ones they are. So how do you get frequency from period? Frequency equals 1 over t. That's a pretty easy one. How do you get period from frequency? It's pretty much the same thing. T equals 1 over f. It's the same formula. They're inverse of one another, so you just boop, 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 boop. What is the formula for a mass spring model? The resonant frequency equals 1 over 2 pi times the square root of k over m. A lot of the questions, all of the questions relating to mass spring models are looking at least in the hand calculation part, are asking you what's happening when either the stiffness, the stiffness, the mass, or the resonant frequency are increased by a factor of something. So if you remember that shortcut that we worked on in class, you're good. You can use that. You have to show your work on these. But you can kind of ignore the 1 over 2 pi and just use the shortcut. If you want to do that, that's fine. Still make sure you show your work. But you don't have to do the whole big thing where you take two equations and equal them out. Although you can, if you want to, and it makes more sense to you. What about the formula for a Helmholtz resonator? It's actually very similar to the mass spring model. The only thing that's different is that instead of 1, we're adding in the speed of sound. So instead of 1, it's 340,000. The 2 pi is still 2 pi, and then we've still got the square root of some numbers. With mass spring, it's the stiffness of the spring and the mass. Remember, K is the stiffness of the spring, M is the mass. With the Helmholtz resonator, the area of the neck is on the top, and then the volume of the bowl and the length of the neck are on the bottom. It's pretty much the same equation. It's just we're swapping some things out. But that's why there's only one resonant frequency for both of those. A Helmholtz resonator is a mass spring model that uses just sound and air instead of like literally a mass and a spring. What about a tube open at two ends? Well, the resonant frequency equals N times 340 over 2L. N, now we have many resonant frequencies, right? So it's a tube. There's many resonant frequencies. I'll ask you for the first 4. So you can put 1 in for N, 2, 3, and 4 in for N. That's what the N is for. And then 340, speed of sound, over 2L. So 340 meters per second. All of your lengths are going to be in meters. And there you go. 2 because we have to multiply the length by 2 to get the lowest frequency that can be resonated by that tube. And then we have to also account for the speed of sound there as well. And then we multiply that by 1, 2, 3, and 4 for the harmonic, for the resonant frequencies. Okay, last one. What about the tube that is closed at one end? A little bit different. 2n minus 1 times 340 over 4L, just like how the other one was over 2L. This is over 4L because we can fit a quarter of a wave into a tube that's closed at one end. So we have to multiply it by 4 to figure out what the lowest frequency is, account for the speed of sound, and then the N is going to give us every other harmonic, because remember, a tube closed at one end, it's a quarter but not a half, 3/4 but not 1, 1 1/4 but not 1 1/2. So it's every other frequency. And that's what this 2n minus 1 is doing also. 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. So you get 1, 3, 5, 7 as your numbers that you're multiplying the fundamental frequency by. Well, it's not fundamental frequency, it's the first resonant frequency. Okay. What does the spectrum of harmonics from the vocal folds look like? We didn't talk a ton about this, and it's going to come up mostly in the next section, but learn it anyway, just in case. It's harmonics that gradually become quieter, or resonant frequencies that gradually become quieter, right? So you've got, it depends on, well, if we're talking about vocal folds, it's always going to be resonant frequencies that become quieter. It's not ever going to be the 100, 200, 300, 400, 500 because it's tube close at one end. So it'll be 100, 300, 500, 700. But they gradually become quieter. Each successive resonant frequency becomes quieter. How does the filter of the pharynx and oral cavity, what does, not how, it says what does the filter of the pharynx and oral cavity do to sound from the vocal folds? It changes it. It amplifies and attenuates harmonics from the sound source. So like different changes to the tube are going to amplify or dampen different harmonics. This means the output into the air is a combination of what? And it is the sound source and the filter. So we have the sound source that's coming out and the filter. That's mostly in the next section. So there's not a ton of that you have to focus on for this exam. This is a picture of that. Here's our harmonics that are coming out of the actual vocal folds, not once they've gone through the tube. So this is what's coming out of the vocal folds. Here's the filter that's set up by the vocal tract, and what comes out are harmonics shaped in this way. And you've got formants or resonance peaks here, here, here. Oh, you can't see me. Here, 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 and here. Those are the formants. So those peaks of resonance are the formants. Okay, last thing is perturbation theory. What maximum is at the open end of a tube? Is it pressure or is it velocity? It's velocity. Velocity is at the open end of a tube. It's a pressure node, which means it's a velocity maximum. And then remember, the reason why I want you to learn the velocity one is because you can turn it into a down arrow. It just becomes its own, direction. Becomes its own set of directions. Make it a down arrow. Max V becomes a down arrow. And that's going to tell you that a constriction at a max V makes the resonant frequency increase, decrease, or stay the same. Decrease or lower. I forgot what I put in there. So constriction at max V makes the resonant frequency lower. That's why it's a down arrow. So you got the max V. If a perturbation lands on or is close to a max V, it's going to make the resonant frequency lower. If it's closer to a velocity node, it's going to get higher. And so let's look at this arrow. Well, here's all the places where you have max V's and max P's. Behind my head, there's a max P. So max V at one end, max P at the other. For the next resonant frequency in this tube, you've got max P still at the closed end, then a max V here, a max P here, and a max V at the end. And then for the third resonant frequency, you've got max P at the closed end, max V, max P, max V, max P, and then, of course, a max V at the open end. So I'm going to throw this perturbation, this constriction. The tongue is getting tighter here, closer to the, it's so far back it'd be like the tongue is getting closer to the pharyngeal wall back there, like as far back to the vocal folds as we have it. But what's going to happen to the resonant frequencies based on where that perturbation is? So for resonant frequency 1, up here at the top, right here, is it going to get higher or lower, and how much? It's going to get higher because it's further away from a max V. It's closer to a velocity node. So velocity node is going to get higher. It's not right on the node, so it's not like a huge increase, but it's an increase. So increase of frequency there. And then we're going to move to this one, the second resonant frequency, are we increasing or decreasing? Hard to tell, right? It's kind of halfway between a max V and a max P. So I would say no change on this one. No change to the second resonant frequency. And then down here in the third resonant frequency, up or down. This is a large decrease. And I've got these answers here for you to look at as well. So this is a large decrease because it's right on the max V. This is an increase because it's pretty close to the max P or to the velocity node, but it's not right on it. So I only put large increase or decrease when it's right on the thing, when it's right on the velocity max or the velocity node. Otherwise, it's an increase or a decrease. And then there's sometimes a slight increase or a slight decrease. That's when it's like close to the middle, but you can still kind of tell where it is. And no change when it's right on the center. Like I said in class, these will never, the thing that decides the answer is never going to be like, in this case, this one. Like you're never going to have one that says increase, slight increase, and large decrease. And then you have another one that says increase, slight decrease, large decrease. Like where these two that are very obvious are the same, and then this one is kind of up to interpretation. I don't have those in the exam, so don't focus too much. If you think it's a slight increase, like that could also be a slight decrease or no change, so don't base your answer on these ones that are hard to tell. Base it on the ones that are like very obvious. But then remember that a max V is not the same thing as a max P. They're totally different. Max V is frequency down, max P is frequency up. Max P is velocity node. Same thing as velocity node. Okay, that's it. Good luck.